Alright, so it seems that we are in the bug tracking phase of the quarter. So some of you don't see the Thursday lecture on your timetable. Does anybody see the Thursday lecture on the timetable? Good. It's an interesting thing. Did you at any moment see the Thursday lecture on your timetable? No?
Yes, at the beginning of the first quarter.
So when you signed up, it was still there?
Yeah.
Because I assume that something went wrong when they changed the rooms. They had first given us a cozy room for 48 people. And then at some point, the student registration numbers did not quite match with that. So then I screwed up in two ways. One is apparently I didn't write flux in front of the room numbers. So the Thursday 103 is in the flux building. So it's in the other direction of campus, and it's a double room, so it's 103/104. And also I learned that the link on Canvas is not correct. So on Canvas, the text that's written there is correct, but the hyperlink is not correct. Okay. Good. So I was talking about Caesar and saying, well, we've now translated to math as something where it doesn't get any more secure. So what are the problems with Caesar? So the first thing, given that all of you have laptops, you notice that 26 different keys is just not enough. I mean, with all the symbols, you would get a lot of permutation, different assignments, but with Caesar you have only 26 different keys. We can try all. And then you assume that the text that somebody sent was natural language, so if you have all 26 ciphertext and plain text in front of you, like 26 like identity, shift by 1, shift by 2, shift by 3, and so on. You look at those 26, and then being human, you figure out which of those is the correct plain text. Another thing which, well, given that it's so easy to do the first part, you might think, oh, it's not your main avenue, but it's something I will need for the next round. Namely, I've already talked about the distribution of letters. So some letters appear more often. So some letters appear much more than others. For instance, if you look at English text, then you're getting the letter E with 13% of the text. That's a lot of the text. And if you look at the distribution, then you have like A at somewhere at like 8%, and you have E at 13%, and then you have B doesn't have much, C happens a bit more, D doesn't have much, E then there's a huge spike, and then nothing really interesting. Well, okay, there's some H and I which appear, and then at some point you're getting N, not quite as high as this, and then you're getting one kind of very characteristic pattern, which is like the R is T triple. So R, S, and T all appear quite frequently in the English language, like each definite article gives you a T, you have lots of letters S and R, and so if you have whatever noise is down here, there are fixed distance between some verbs, some strong spikes here. And you'll see 3 spikes together, you'll see a single spike in E, which is higher than everything else. And of course you will see these distributions only when you have sufficiently long text. On Thursday in the exercise, I'll give you one text which is just like artificially made up so that, of course, all the frequency distributions are not looking like the normal thing. So the most frequent letter, I don't know, is going to be Q or something. No, it's not Q. I'm not giving away the solution this easily. But normally, if you have like a normal, if you have some text, you see a distribution which is very characteristic. The distribution has strong peaks at, well, the strongest I would say E. Well, the strongest is at E, and then you see strong ones at N, T, well, R is T, and including the triple peak for RST. So what you do is you take the Caesar cipher, and it doesn't matter whether it's represented as letters or as numbers. You do frequency analysis on this, and you look at how the ciphertext symbols, how often those appear. And then, well, okay, if there's some which appear very frequently, and they're close together, those are very likely the candidates for RST. Then we look, however many letters this is, before where the N would be, see whether that one is frequent, look where the E would be, and then it's likely the right thing. So instead of going through the pain to translate it, which at least in the old days people thought was more pain than doing frequency analysis, you would do some counting, then figure out whether the peaks match, and if not, then try something else. So including the triple peak there and the fixed distances. The reason I'm mentioning those is that another of the old ciphers, so today we're not going to do anything about, so I mentioned at the beginning we want confidentiality, we want integrity, we want authenticity. So today we're only covering confidentiality. We're not having anything in there yet that Bob would know it comes from Alice. We don't have anything in there that protects the ciphertext being tampered. So at this moment we only assume that Eve is a passive and eavesdropper who will not inject any message, will not modify the message. So the only target for today is dealing with confidentiality, and all the old systems deal with it in the not optimal way. So another old one is the system due to Viginere. Now Viginere is interesting in that you can dial up the complexity of that. So Viginere is like Caesar, but with a pass or with a key word instead of a key. So uses a Caesar with keyword. And that means you have, well, let's all agree that crypto is a cool word, so crypto is going to be our keyword. So let's do this as an example. K is crypto. And then this means that the first letter will be encrypted such that A goes to C. The second letter will be encrypted so that A goes to R. So that's where our Caesar comes in. This means A goes to Y. This means P goes to Y. A goes to Y. A goes to P. A goes to T. And A goes to O. So, meaning that the first letter uses A goes to C, second A goes to R, and then say third A goes to Y, etc. Now, your message is going to be longer than 6 letters. So once you're at the end, you have 6 letters. The 7th letter is again using A goes to C. 8 is using A goes to R. 9th is using A goes to Y. So 7 uses A goes to R, C. 8, A goes to R, etc. So it's like you're writing crypto under it all the time. So if you, for instance, want to encrypt, this is a bit better. Then, all right, now we use our dial thing here again. The first means A goes to C for crypto. A goes to C, so that means T goes to V. Then H is encrypted under A goes to R, so I dial A goes to R. A goes to R, and now H goes to Y. Then A goes to Y. A goes to Y, and then I on this goes to G. To one more, A goes to P. And then S under this goes to H. Now, I'm going like, these are the first 6 letters. Now this one is going for the A goes to C. Convenient enough, this is an A, so this one goes to C. Then here I'm in the A goes to R. Now B is the next letter, so we go into S, etc. Now, for doing this, of course, it's cumbersome because you're changing the whole time. But if you understand Caesar, and particularly if you're doing Caesar with numbers, then this just means you're writing the numbers corresponding to crypto under it repeatedly, and you're just adding mod 26. So this is getting a bit easier. Just like more convenient with numbers. But is it more secure? Now that depends on how long the keyword is. If your keyword is as long as the ciphertext, then for each letter you have chosen a totally different encryption. So the security depends on the length, so the size of K. If the length of K is the same as the length of M, then each position encrypts independently. And that would mean it's secure. Now, how you get such a long text? So one thing is, of course, you might send very short messages, then something like crypto or crypto is cool or some short sentences, okay. But a problem arises when you have a long message, or you want to agree that you want to send arbitrary length messages. So then you might agree on, like, we all use a particular novel from Sherlock Holmes, which you all like, and then we agree today you use page 10, tomorrow we use page 13, so we jump around. But then actually you don't have really independent things, but then you're again getting frequencies from the English language in there. Because now that we have Sherlock Holmes coming in there, then it's kind of some dependencies. But it gets a lot harder to decrypt. Let's assume for like us, for an easy, let's say mostly, but let's assume for us now that k is much shorter. K is much shorter than the message length. Now, if you know how long m is, say somebody knows that we agreed on a 6-letter word for our keyword. They don't know what the keyword is, but they know it has 6 letters. Then they can go back to how we break in Caesar. Well, you could try it all for each of the 26, but that gives you starting to get lots of combinations. I mean, for each of those you have to try 26. So you get a 26 to the 6 combination. Well, that's still doable with your computer. Let's assume you have a keyword of length 10 or 100 or whatever. Then it gets rather cumbersome. But you can also do the second one. You can do frequency analysis by skipping all the time. So if you know it has length 10, you just do frequency analysis on your ciphertext of every 10th character. Now let's assume you're getting 20 pages of ciphertext, then that will be still good enough to see statistics like this. So if k is known, if the length of k is known and very small, and just try all 26 to the length of k possibilities. Now, interestingly else, we can do frequency analysis on, you do it for the 6, you do it on the 1st, 7th, 13th, 19th, and so on. Then you get one frequency spectrum and you figure out, oh, this was using A shifted to C. And then you do another one, you do on the 2nd, 8th, 14th, 20th, and so on. Next frequency analysis, and if it's long enough, you're going to find out how its A goes to R. So do frequency analysis on first length of k plus 1, 2 times length of k plus 1, etc. to figure out. First shift then on second length of k plus 2, 2 times length of k plus 2, etc. For second shift, now, as I said, this needs a long enough ciphertext, but it's doable even, I mean, this one scales with the length of the ciphertext, whereas this one scales with the length of the keyword. Here it's linear in the length of the keyword, here it's exponential in the length of the keyword. So this one we have to do for each letter in the keyword, but only, well, length of k times. Here, if we increase length of k by 1, it will be 26 times as hard. So here, even with stupid Caesar cipher, well, use the Viginere, you can actually exhaust the computer, whereas for this one, as long as your ciphertext is long enough, you have a good chance of doing it. So this takes time. Linear in the length of keyword. Wow. Above. Is exponential the length of the key. Now, all of those, we're assuming that we know the length. What if you don't know the length? You can be assuming it's not super, super long. You can assume it's something like 5 to 10 because, well, it's done by humans and humans are lazy and you don't want to count too many positions ahead. But how can you figure out whether it was 5, 7, 9 or anything? What you don't know how long the keyword is. Any ideas? Yeah.
Well, you can rule out certain lengths. If there's like an A and then an A and spaced after, and they have different encryptions, then you can say, well, it's not this.
I get an idea of where you're going, but I'm not sure other people understood it. So I assume you're looking for like fixed patterns.
Yeah.
So what he's getting is, let's assume you have a really, really long text. Now, in the long text, you'll see the a lot of times. And now it depends on how the aligns with, say, our keyword crypto. Maybe at the beginning, it will be perfectly aligned. So you're encrypting the by A to C, A to R, A to Y. But the next time that you're encrypting the, it aligns with these three, or with these three, or with these three. So there are like 6 different ways that the letter the could align. But it means every 6th time it will align nicely. Now, if it aligns, then they will always encrypt to the same way. So if the under these encrypts to these 3 letters, you will see these 3 letters again over here. And if it's something as frequent as the in English texts, then on your page, every 6th time it will be the same way. You will see those 3 letters together quite a few times. So if you're looking through your text and you're finding repeated combinations of letters, then that's probably at the distance, which is a multiple of the keyword. Now you were saying I can rule out something. So I'm not quite sure how I would rule out, because it could be like I'm seeing that at distance I'm seeing that at distance 60. That probably rules out 7, but I get no idea whether it's 5 or 6 or 3. But okay, no, you're right. I mean, it does rule out some things. It would rule out 7, it would rule out 9. So if I see some combinations at distances that are not divisible by certain numbers, then I don't get it. I don't have that length. So search for repeated combinations of letters. Those are likely encryptions of the same combination of plain text. And so the important part about this is that they probably align in the same position of the keyword. That means they align and then we see, okay, it's distance 60, and that means our keyword 60 positions later was exactly in the same position. So that means between here and 60 later, we filled an integer multiple times the keyword. Now that can mean lots of things. It could mean it's length 5, it could mean length 6, it could mean length 12, but yes, it does not mean length 7. Thus, the distance is a multiple of k. So we can check devices. Now, we have our 30, we have our 60, and we can do more of this. We can now look for other combinations, and maybe we find one other three-letter thing which repeats after 18. Now 18 is not divisible by 5, so we can rule out 5. But maybe we'll try all kinds of those things, or text is not long enough, then we still don't know whether it's 5 or 6 or 10. How can we ever figure out what the length is? What are good ways there? Yeah?
Just try all. It's only 3, then.
It's only, yeah, it's trying.
Difficult to try all.
But if we try them all, then what do you mean by trying? Like
Well,
how do I
if
figure
it
out
can
which
only
one?
be 6, 5, and 10,
Mhm.
then it's just 3 times as much work as just doing one. And that's not that much more.
It goes in the right direction, but how do you figure out it's correct?
Well, if you get correct text out, then it's correct, but you can also look at the frequency. If
Yeah.
the frequency corresponds to the English language, then it's probably also correct.
Yeah. So the thing is, yes, you could do 3 or 10 or whatever times as much work, but if you don't even know what the shifting distance is, then you're likely to getting a problem with identifying the right piece. So if you're betting on shifting distance 5, but it's shifting distance 6, you will not get a nice one. Now that could either mean it's strange text, but much more likely it means this is not the right distance. So if you analyzed letter 1 and then letter 6 and then letter 11 instead of 1, 7, 13, and you don't see nice spikes, then you also have an indication it's not the right shifting distance. So typically you would try something, that's correct, but then you abort very early because you don't see spikes. Now, spikes alone don't tell you everything. It's hard for the spikes to distinguish between length 6 and length 12. And even at length 3, you would probably still see something, but it wouldn't be so clear. So you're still running around with like divisors and multiples. So to test the candidate length, you're going to do a frequency analysis. As before. And then we're going to abort if we don't see nice spikes. And of course you could try, like if you're getting a guess for 12 instead of a 6, then you will find out that your keyword ends up being crypto, which just means you've done twice as much work as you should have done, but it will still be correct. Yeah.
But if you start with the small numbers and go up, then you go
Yeah.
at that point.
If you start with the small numbers, then you might end up in a situation where your peaks are not as extreme because you're getting like an overlap between one distribution and another one, but you will still see kind of some spikes. So you basically have two distributions. You will have the distributions of A goes to C overlapping with the distribution of A goes to P. So that means you have this guy and another one shifted. And depending on the length of your text, you might be misled to thinking it's the correct one. But then you'll try for the next letter, and then they're further apart. So assuming that your text is long enough, it always gives inverse frequency analysis. Some small issues with multiples and divisors of length. But usually, this is pretty much both. And if you're not sure, I mean, you can still resort to trying things. For instance, if you really think it's key length 3, you can try all 26 to the 3 positions, see where they go, if anything reasonable comes out. But, well, you won't want to try this for 12. Okay, so much for Viginere. So that's basically a way how you can turn Caesar into something more reasonable. The super long key will come up again on Thursday when we're looking at one-time heads, but there are a bunch more funny ones. So because this first part with all the figuring out the distances, this part, figuring out the distances where you're looking for repeated parts or you're looking for digraphs in normal Caesar or in the symbols, a system called Playfair Cipher tries to avoid all digraphs. So what we've done so far is we've been keeping letter combinations that were together, they stay together. In the Viginere version, they might be decrypted in different ways, but they don't change position. Now, Playfair has the idea of moving things around a little bit. So there's a preparation step. So from the left, you group the letters in pairs. And if you have a repeated letter, you insert an X. Okay? And then also we're going to append an X if we have an odd length. Now to explain why I say from the left, let me do this as an example on hello. Carefully chosen to have a repetition of letters. Now you look at this thing and you say, oh, this has odd length. Let's append an X. But that means you're not going from the left and you don't do the pairing. So I'm grabbing those two letters. Okay. Now I'm having a group of letters which is a repetition. So I'm supposed to take the first pair. That's okay. Then I'm taking L and I'm inserting an X. Now that's a pair. And now LO is actually a pair. So I've turned an odd length word into an even length word. So I don't do the append at the beginning, I do it at the end if there's some singleton. Okay, that was just a preparation that there's no encryption here. Now, Playfair uses a key word or sentence. Let's do this for an example. Let's do this for top secret. And then it works with a 5 by 5 matrix or square. Okay. 5. And then we fill this keyword in from left top corner to bottom right corner, and we leave out repeated letters. So once I get to the E here, I have already used E before, so I skip it. Once I get to the T here, I'll skip it. So fill in from top left. Skip letters that repeat. And we're also going to put I equals J. That's why we can deal with 25 rather than 26. Okay, so T, O, P, S, E. And now E and T have already happened. And then I fill up with the letters of the alphabet in sequence that I haven't used. Then fill in the remaining letters alphabetically. And again, no repetitions. Okay, I haven't used A yet, so it goes here. I haven't used B yet, it goes here. C I have, D I haven't yet, E is there, F, G, H, I, J is the same as I, so that doesn't get in there. K, L, M, N, O is used already, P is used already. Q isn't there, R should be there, S is there, T is there, U, V, W, X, Y, Z. Always happy at the moment when the alphabet is no longer or no shorter than it should be. Okay, so that is now our super secret Playfair encryption scheme. Now, how do we use this? So, you have encrypt the plain text tuple. First case, if those letters in the same row are the same row, then we're going to shift to the right. If they're in the same column, I have to look whether it's shift up or down. I think it's shift down. Oh, I should write rotate because you're moving in from the other side. And then else, if you have two letters which are not in the same column or row, then you span a rectangle. So if you, for instance, have C and H, then you have a rectangle which goes C till A, down to H, and over to F. So then C and H span a rectangle, and you encrypt by moving to the other corner in the same column. The alpha letters span a rectangle. And then you encrypt to letter in corner in the same column. Okay, so if you look at our hello again, so there was L and then the inserted X, and now we also understand why we have to insert a letter, because, well, double L wouldn't be encryptable. So then our hello, the H and the E are in the case of in the corners, so that's the 3 by 3 up in the upper corner. So then the H goes to P and the E goes to K. I seem to disagree with my notes. Consistency is more important than notes. So, okay, L and X. L is there, X in the bottom corner. So L goes to V, X goes to N. And then L and O. Look, O is up there, so L goes to T, and O goes to M. It looks like we're doing in order to make the last example work, let me just change this to row. And then we have K, P, N, B, and T. Because I wanted to give you an example. So if you're decrypting ET, DL, BG, and SV. Now, decryption works the same way, except for in reverse. So if you're saying ET, then E and T are in the same row. So you got to E and T by having done a right shift. So you're doing a left shift again. So E comes from S, and T comes from E. And DL, D and L are over there. So D was in the same row, not column, sorry, and L was in the same row. So D comes from C and L comes from U. Do you see what BG comes from? You see BG over there?
Oh, this is on.
Here R and I, okay. You can see what's coming out. Finally S and V, so S is up there, V is all the way down the corner. So S comes from T and V comes from Y. Okay. Sorry for the confusion with row and columns. I mean, as long as you and your encryption partner know which one you choose, it's obviously working consistently. I don't know why I chose different microaggression.
Oh.
Anyway, so I hope that all of you can come on Thursdays. If not, I'll try to have the camera again. But I won't have camera for the exercise sessions. The exercise sheets will be online on Thursday before the lecture, before the exercise session, so you should have them on your laptop when we start. Fine, that's it for today.